let's see how we did with some of our new information. So how can we change our formula to represent the difference in the number of people affected per day? What do you think your new equation will be? So let's take a look at the new information that we were given. I'm going to start by setting up a table with some x and y values here. So what we know is we don't know where it exactly started, but we do know that today in Alexandria, after day 1, that there are 21 people infected. The other information that we've been given is that it is increasing at a rate of 50% every day. So if our growth rate is an increase, that'd be plus 50% every day. So that makes our growth factor, we have our 100% that it starts at, and then if it's growing by 50% per day, keep in mind that we cannot calculate with percents, so we need to change these both to decimals. So that'd be 1.0 plus 0 and 5/10. So that means our growth factor would be 1 and 5/10. So then that means from here to here, it's going to grow by 1 and 5/10. So therefore, on day 2, we know that it would be 21 times 1.5 would be 31.5. Now, in order to get our original value for what it was when it initially started, since we're going to be multiplying by 1.5, we could do the inverse, which would be to divide by 1.5. So if we take 21 divided by 1.5, we find out that on day 0, which would have been AKA yesterday, that there were 14. So identifying our values, this is our A value for the equation. Our growth factor is our B value. So our equation would be 14 times a growth factor of 1.5 to the power of x, where x represents the number of days and y is representing our number of people infected. So when will the entire population be infected? Well, the entire population of the world is around 7.5 billion. So let's try some different values and let's see what we can come up with by plugging in the number of days. So let's see what might happen after 30 days. So if we do y equals 14 times our growth factor of 1.5 raised to the power of 30. And let's see what we get. After 30 days, we get 2,684,514 people. So definitely not our 7.5 billion that we need when we're still talking millions. So let's try what happens after 40 days. And after 40 days, we get so you can see we're getting a little bit closer here. After 40 days, we get 154,802,652, but still not 7.5 billion. So if we keep trying some more values, and we're trying to get to that 7.5 million mark, let's try closer to 50 this time around. And when we plug in 50, we're going to finally hit our mark here. So we get 8,926,701,003. Now that's obviously a little bit too high. So when we talk about when will the entire population be affected, so that would be between day 49, which would come before it, and day 50. We find that by substituting and plugging in values for x. So now let's talk about what would be a reasonable domain for this question. We'll recall that our domains are our x values, and our x values are being represented by the number of days. So if our entire population is being infected between days 49 and day 50, then it would be from 0 is less than x is less than 50. Now, when we talk about a reasonable range, recall that our range is in fact our y values. So we have to look at how far the graph is rising. So we know that the lowest that it can go is our lowest y value here is going to be 14. So it's 14 is less than y is less than. Now y, remember, is our population of people infected. So we started with 14, it'll never drop below that, and we're talking about 7.5 billion people. Okay, check your answers, see how you did, and make any corrections that you need to.